Maurice de Groot was the first head of the statistics department here at Carnegie Mellon, and he wrote this excellent, excellent book. If you're interested in general reference book on probability and statistics, that's the first thing I go to as a reference book. We have a lot of de Groot stuff here. We have a de Groot Memorial Lecture, and he's really left his mark on the department and on the university. I should mention, and I'll mention it many other times, that CMU has one of the best statistics departments in the country and in the world. It's really a top place for statistics. Larry Wasserman is a buddy of mine, a current professor in the Department of Statistics, who wrote a book with a modest-sounding name, All of Statistics. It's a very nice, I'll bring them next time so you can see them, a very nice hot pink cover book. And a few years later, he kind of contradicted himself and wrote another book, but this one called All of Non-Parametric Statistics. So actually, this is all of parametric statistics, and this is all of non-parametric statistics. We'll talk a lot about parametric and non-parametric statistics. And then there are going to be a bunch of individual articles that I will point you to. Usually, they're going to be hanging off of the web page. So on the web page, you'll find the schedule, and you will find, for each lecture, recommended reading and required reading. So it's up to you how much you're going to get out of things, but the required reading would really, really help you with the material. I'll give you a very brief overview of what we're going to do. We already did the grand thoughts part, although we're going to sprinkle grand thoughts throughout the lectures. Today, we're going to talk about the source channel formulation, sort of tie everything else that we're going to do here into specific problems in language technologies. Remember, this is originally a Language Technology Institute course, so we're a lot about language technologies. We're more about language technologies than we are about linguistics per se. Linguistics, of course, plays a role, but it's usually more of a motivating role and an inspiring role rather than we're not going to debate different linguistic theories here. We're mostly going to debate different statistical methodologies and how they are applied to help language technologies. Those of you who are from outside LTI may wonder what in the world is a language technology. So language technologies are things like speech recognition, automatic computer speech recognition, machine translation, information retrieval, question answering, automatic document classification, anything that you do automatically with language. Machine learning applied to language, what you do for the betterment of mankind or at least one person. So source channel formulation is common to most language technologies. So we're going to discuss it. And then we're going to start from the very bottom of language, or maybe it's not the very bottom, but we're going to start from words. Talk about words, the distribution in natural language, make a distinction between word types and word tokens, talk about Zipf's distribution, Mandelbrot distributions, and heterogeneity of language. And then we're going to start on our first real statistical problem, which is how do you model word distributions. So you have a finite amount of text, and you want to estimate the probability of words. And the probability of a word is not the same as its frequency in the particular corpus. Like if a word occurred 3 times in a particular corpus of size million, it doesn't mean its true probability, and we'll talk about what it means, the true probability, doesn't mean that it's 3 over a million. It could be higher, it could be lower. So we're going to have to deal with this issue of estimation from a finite amount of data, which is a huge part of statistics. We're going to focus specifically on estimation in sparse domains, where the number of examples you have is very small. If you had 50,000 occurrences out of a million, then 50,000 over a million is a pretty good estimate. But if you have 1 occurrence in a million, then 1 over a million may not be a good estimate. In fact, I'll show you that it isn't. It's a lousy estimate. So we'll come up with better estimates. This would lead to discussions of estimation in sparse domains in general. We'll talk about different kinds of estimators, the maximum likelihood estimator, which is a very common kind of estimator used in statistics. Talk about what to do with things that never occurred, the zero frequency problem, smoothing, shrinkage, good Turing formula. It's going to spend quite a bit of time dealing with this very, very simple issue of modeling a simple multinomial over words. And when we're done with dealing with multinomials over individual words, which are called unigrams, we're going to talk about n-grams, which are, in statistical perspective, they are basically conditional distributions. And if you thought the unigrams were sparse, the n-grams are a lot sparser, doubly as sparse or exponentially as sparse. So now we're going to deal with really, really sparse domains and what we do about them, and deal with different methods that were developed for them. We'll talk a little bit about, maybe a lot, about information theory, concepts from information theory, like entropy, Gale divergence, measuring the entropy or estimating the entropy of natural language, and alternative measures of success, alternative measures of goodness of models. We'll talk about clustering, which is one method of dealing with sparseness of data, applied to specific language problems. When you apply clustering to n-grams, you get class-based n-grams. You can have hierarchical clustering. You can have hard and soft clustering. A hard clustering is when every member of a set belongs to exactly one cluster. A soft clustering is when they can belong partially to different clusters. And this would lead to, the soft clustering would lead to a specific case of a much more general class of problems known as latent variable models. So latent variable models play a big role in statistics and statistical estimation, because very often when we model things, not just language, it makes sense to posit that there are some unobserved intermediate variables that are part of the structure of the model. But if they're not observed, it's very hard to estimate their effect, and when they're present, that's the latent. Latent means hidden or not visible, not evident. So we'll introduce a family of algorithms called the EM algorithms that you may have heard of, that are specifically meant to deal with latent variables. We will talk about one particular form of latent variable model called hidden Markov model, which is very, very useful in many language technologies, and show specific examples of how hidden Markov models are used, for example, in part of speech tagging, in word sense disambiguation, in speech recognition. Then we'll talk about decision and regression trees. So we're not going to introduce decision trees. I'm going to assume that you all know what they are. Those of you who don't know what they are, I will cover them very briefly, very fast. And if you don't know, come to me, and I will happily give you a private lecture. What I'm going to focus on is usually decision trees and regression trees are used in the context of attributes of data, numerical data. It's very, very strange to apply them to language. Language is a very, very weird kind of thing. It's categorical, but it's not exactly categorical. It's variable length. It has all sorts of structures. So we're going to deal with the challenge of applying them to language. And then we'll talk about stochastic grammars, and that's the closest we're going to get to real linguistic theories. I mean, we can philosophize and argue about linguistic theories. That we will do. But as far as applying them to, in the context of the material of the course, the closest we're going to get is context-free grammars. And the probabilistic version of context-free grammars is called stochastic context-free grammars. That's what the SCFG is here. Either a stochastic context-free grammar or probabilistic context-free grammar. It's the same thing. And we use that to introduce another form of the EM algorithm called the inside-outside algorithm. And apply to another kind of grammar called link grammar, which is effectively a context-free grammar. We'll talk about maximum entropy, the maximum entropy principle, maximum entropy modeling, exponential models, how to induce features, language model adaptation, talk about specific properties of language, that it's very bursty, namely rare things happen all the time. Think about it, rare things are very common in language. Just about every other word I say is fairly rare, by some definition of rare. And of course, it's not as contradictory as it sounds, because if there are many, many, many rare things, then some of them are bound to happen all the time. But the other funny thing about language is that when a rare thing happens, it stops being rare. It starts being common. I don't know how many of you have heard of, well, let's take a bad example, Sandy Hook. We haven't. That's the elementary school in Connecticut where horrible shooting occurred recently. It was never in the newspaper. Maybe if it was 1 in a billion. But once it showed up, it became very common. Right? That's true in many locations. You know, if there's an earthquake somewhere in the world, all of a sudden a town that nobody has ever heard of is in the news all the time. So I call that burstiness. Other people call it that too. The phenomena that it's not just names of locations. It's even terms that are just not commonly used. If you find that somebody writes a letter and they are astounded to find something, if they use the word astounded in the letter, there's a much higher chance that the word astounded will occur again, or to astound, or astounding, will occur later again in the same letter than its general general frequency in the language.
Maybe
So,
an example of this would be trending topics on Twitter.
absolutely, that would be a very strong example. But I was trying to give examples outside the genre of language called news or sort of fashionable discussion. So it's definitely true in news, and it's definitely true in areas where opinions come and prevail and topics become fashionable and so forth. But even if you take this out, if you take like fixed literature, Shakespeare literature, and you take one fixed work, you will find that once a word was mentioned, it is far more likely to be mentioned again than before that. Words tend to occur in bursts. And if you apply to the lemma of the word, to the basic form of the word, it's even stronger. Yes.
I have like related research about this, but I work on like in conversational data, like two people conversation, and like we try in like 3 different languages, and this kind of burst phenomenon does exist. So, yeah.
Yes, absolutely. Thanks for bringing it up. In conversational language, there's another interesting phenomena that people adjust their lexical choices to one another. So I may use the word big or the word large in a conversation, but if I chose one of them, and you respond to me, and you have to and you want to use one of these words, you're more likely to use the word that I used without even thinking about it. It primes it in your mind. It is a way of showing, sort of forming a bond of some sort, a social bond by using same terminology. So there's a very strong phenomenon of people affecting each other, even if they're in the same sort of same place in the hierarchy. If it's not a boss employee or a parent-child, even if it's a very even kind of relationship, there's a lot of borrowing from one another.
There's a nice thesis by Christian Niculescu on this very topic about the whole linguistic coordination.
And he's here now.
Is he? Oh,
Yeah,
okay.
it's a new faculty. Okay, I think. Okay, so that I went on a tangent talking about adaptation, why it's needed. We'll talk about dimensionality reduction. So language does not lend itself easily to dimensions. Many problems in statistics and probability theory can be visualized as Cartesian spaces, sometimes high-dimensional Cartesian spaces. And we are actually pretty good at thinking about Cartesian spaces. We have a notion of distance in the Cartesian space, of rotation, of scaling up and down. Language doesn't fit very well into these kind of spaces, but you can still talk about dimensionality of language. In fact, you can make a pretty strong quantitative argument that some topics have higher dimensionality than others. So we'll talk about that towards the end of the course, and we'll talk about syntactic language models that maybe go a step beyond the context-free grammars. So believe it or not, we're going to cover all of that in the semester, and probably a lot more. What else do I want to tell you? I think this is it. Oh, yeah. Assignments are going to be out roughly once a week. And most of them we try to make open-ended. Maybe not all of them, but some of them open-ended. So it's up to you to find a data set and up to you to do something with it. But they're all meant to give you practice in the same thing that we're talking about. No, I wouldn't say most of them, but a good number of them are open-ended. And then towards the end of the course, there will be a project. And the project is the same project definition for everybody, but you're free to go off and do whatever you want with it. It's very, very flexible and wide. Please work in a team of, I think, 4 people would be ideal. You're not graded against each other. And I should add, when you talk about grades, that it's not hard to get an A in this course. Most people do. You're not graded against each other, but chocolate truffles would only go to the best team. So those of you who were here last year know that this is a tradition. I do give out chocolate truffles to the best team. And if there are 2 criteria, then there's chocolate truffles to the team that did best in each one of the criteria. So it's a competition in that sense, a very friendly, kind of humorous competition, but it's not a competition of grades. So don't worry about that part. Okay? Any more questions? Please. Thank you. So there is no midterm and there's no final. What there is a 3/4 term. So there will be an exam somewhere about 75 to 80% of the way into the course. We'll set the exact date shortly. It'll cover all the material up to that point, because after that there's going to be a little bit of material that we wouldn't have time to cover, and then there's going to be the presentation of the courses. So I forgot to mention that every team will get a small number of minutes, like 12 minutes or so, to present the course at the end to everybody, and it's a very friendly kind of thing where people exchange information and notes, and so that's the hands-on part. So sometime before that, like 2 weeks before that or so, there's going to be an exam.
All the homework's graded?
All the homework is...
They're open-ended?
Maybe I overstated how open-ended they are. The first 2 or 3 or 4 are open-ended, but there are certainly several homeworks that are not open-ended. Some of the homework involve programming. So I should warn you in advance, although it's not usually a problem for this class, but at least one of them, when we discuss hidden Markov models. Hidden Markov models are extremely useful, and you really need to learn them and understand them. And I remember from my own experience that it took me several times of it being explained to me and trying it until I really got it. And the only way you really get something is when you actually try to do it. So for that reason, I insist on everybody actually implementing a hidden Markov model training program. Okay? And that's going to be the most, programming-wise, the most challenging part. Not because it's a lot of code, but it's because chances are you will be up at least one night banging your head against it until you figure out the bugs. But it never fails when I give people exit interviews at the end. They never fails. They always say, yes, they understand it so much better now. And even if they thought they understood it well before the assignment, after the assignment they said, no, we thought we understood it, now we really understand it. So there are different levels of understanding. So I do think it's really important. Now, I mentioned that this class is, for the first time, has a significant number of non-LTI and maybe non-SCS people. So for them, the programming might be somewhat challenging, and I will work with you because I want to keep that class open to people outside SCS as well. So CMU thinks of itself as a place where everybody programs and stuff, but and they may very well be. But if you do have a problem with that, it's a good question of how long would you say this program is, if you remember, how many lines of code? Michael? For HMM? For HMM?
Usually it's depends on the language you use, but if you use MATLAB or Python, usually it shouldn't go over 100 lines.
Oh, really? In 100 lines you can do it. Okay, that's not too bad. No, there's just one assignment when you do HMM. So this is the most demanding assignment programming-wise. And it'll be 100 lines. Okay, so if you can write a program of 100 lines, I think it took me a lot more than that when I wrote it myself, because I wrote in a stupid language like C or Fortran or Copilot. So, you know, so all the input and output and all of that. But the algorithms themselves are pretty succinct. So that's a warning, but don't let it scare you away. I don't want you to go away. Stay in here. If you're thinking of going away because of that, come and talk to me. We'll work up another solution. Okay? Anything else?
What is the grade breakdown?
Most people get an A.
Percentage of conversions in the
I don't remember. It's on the web page. The exam is only 40%, the assignment is another 30%, and the final project is 30%. And you can get extra credit for class participation, but most people participate, so most people get extra credit, which is why most people get an A. Some people get a B, and most people, I know masters need to get at least a B to pass. So C is kind of like a failure, and I don't like giving that, but I also sort of will use my sort of, it will be unconscionable to give someone a passing grade if they didn't pass, but it doesn't usually happen. Okay?
You tell us something about the nature of the project that you will be working on, or you haven't decided?
We haven't decided yet. Historically, I've used 2 or 3 projects and kind of cycled through them. So to keep it more interesting, and but I'll give you some examples of projects. Well, we need to go a little bit further in the material to do that. But the idea is that the project is open-ended. It's performance-based, so you know how well you're doing on a test set and an evaluation set and all of that. But you're free to use any technique that you want. Open in that regard.
So it's probably somewhat along the lines of a shared task.
Of a what?
Of a shared task on some topic.
Yeah, yeah. And with the shared training data and shared evaluation metric. Okay. So let's get rid of this silly PowerPoint. Let's go up. Nope. No, we don't need to do that. We don't need to do that. There's not much sun today. But I'll get, yeah, I know. But sometimes it's also on the board. Okay, so in all of our work, we're going to make sort of adopt a fiction. And the fiction is that language comes from a probabilistic source, namely that language has a distribution. What do I mean by that? We will imagine language as something that comes at you from some source, and you push a button and you get a word or a sentence or a document or a paragraph. You get some unit. And you push the button again and you get another one. And we're going to think about it as a probabilistic source, namely that the word that you're going to get next comes from some distribution. We're not going to assume the distribution is fixed. So the word you got now might affect what word you're going to get next, and it might change over time. There are going to be lots of variations. But we're going to assume that language can be thought of as a probabilistic source. And linguists already will object to that, because to them, language is something that comes from a human context and from thoughts in your mind and intentions, and all that's translated into syntactic choices and lexical choices and then articulation. It's a very complex human behavior. How can you capture it in the probability distribution? And of course, they're right. But the answer is you can capture anything in the probabilistic distribution. The question is, how well do you capture it? Right? So it's an open question how well you can capture language using some kind of probabilistic framework. And the probabilistic framework can include those complicated processes that we talked about. You could come up with a model that includes somebody's thought process and what they just heard and what they know about the world and what they want to say, and then combine it with who they know they're talking to and what they know about their ability to understand and how they translate it into. You can come up with very, very complicated things, but you can make them probabilistic and then estimate parameters for them and so forth. But our biggest abstraction is going to be that we're going to think of language as coming from some distribution over words or over sentences or over paragraphs or over documents or over topics, lots of things. When I say language, I usually mean written, as in text language. Of course, language is also spoken. In fact, language exists in spoken form, as we discussed last time, much before it exists in written form. But usually by language, I mean the written form of the language. Sometimes there will be variations. So the written form of the language is accessible to anybody who sees it. It consists in most languages of words written by characters with spaces between them. Again, there are variations. But since it's accessible and there's no controversy about what the letters are, I would call that the surface form of the language. So I'll use S here, which is different than the S used for sentence. S is the surface form. And then P over S would be a distribution over the surface forms. The surface form, again, could be a word or a sentence or a larger unit. But hiding behind the surface form, there's a much richer world of meaning and of shades and variations. As you all know, language is ambiguous. All natural language is ambiguous. And even the parts that are not ambiguous, it's not immediately apparent from the surface form what the deeper version is. So I'll give you my favorite sentence. Mary saw Jane standing with a telescope by the bank. She waved to her. So those of you who have taken linguistic classes may have seen some variant of this sentence before. I try to pack in as many phenomena as I could. So this is the surface form. It has yea many words, and what the words are is not controversial and is known to everybody. But what the words mean and what the sentence as a whole mean can be ambiguous or controversial. So you suggest sources of ambiguity or yes?
Like the owner of the telescope is
Right. So this is a preposition. So known in linguistics as a prepositional phrase, PP, prepositional phrase. And prepositional phrases attach to something in the rest of the sentence. So the question is, what does with the telescope attach to? Before you started thinking about it, what did you think it attached to? What did you have in your head? Did you have Mary standing with a telescope and seeing Jane? Or did you have Mary standing like this and seeing Jane standing there in the corner with a telescope? Second one? Okay, so it's really ambiguous. I mean, people have different. So this could connect to saw with a telescope, or connect to standing with a telescope. So this is known as the propositional phrase attachment problem. PP attachment. Okay, what about parts of speech? Parts of speech are things like noun, verb, adjective, adverb, preposition, modal, and within noun you can have plural noun, singular noun. Within verb you can have past verb, present verb, but the main parts of speech are noun, verb, adjective, adverb, and a few others. Is it very clear what each word is?
so you could have a very grotesque interpretation of the sentence if you were to mix up part of speeches. When you
Right.
to say Mary, it's like an order, saw Jane while she's standing with the telescope by the bank.
Right, so saw, you did this. Okay, so that's my favorite example here. Saw. How many of you noticed the fact that saw could be a noun in this sentence? I don't mean it to be legal, but how many of you saw the word saw and it occurred to them that the word saw also means this? Just one, two, okay, three. But you were primed, right, because you knew I was looking for ambiguity. If you saw this sentence in everyday language, it wouldn't even occur to you. So there's some process we go through. We take saw, and we know that it's a noun and also a verb, and it doesn't even rise to our consciousness. We immediately rule out some possibilities. So this is an example of part of speech disambiguation. Of part of speech, we call it part of speech tagging, because one of the first things you have to do in language technologies is to tag the parts of speech to tag each word with its correct part of speech, so that further downstream processes can do the right things with them. So if this was tagged incorrectly as a noun, you can imagine that further downstream processes will fail, will do miserably. Okay, so we have part of speech here. What's this? I'm sorry? Okay. Well, what is the bank? What do you have in mind? Did you see a PNC or Mellon, or did you see the Monongahela? Okay, how many saw something like Monongahela in their mind? How many saw PNC or? Okay, that's again quite balanced. I mean, not always will it be balanced. Sometimes it'll be a 90%, 10%, and you think they're weird. But 50-50, that's pretty good. So we call that word sense. Word sense. And the associated technology is called word sense disambiguation. Ambiguation. So what's common here to everything is that this is a prepositional phrase, and the problem is attachment. This is a part of speech, and the problem is to choose which part of speech is right, or to tag it. This is a word sense, and the problem is to disambiguate which word sense is meant. Turn out word senses are not as clearly defined as you would think. You might think that here the word bank has just 2 word senses. But it actually has many more. If you go to a dictionary, you will find an amazing number of word senses. They're usually numbered differently. And usually they come as a hierarchy. So you would have 1A, 1B, 1C, and then 2A, 2B, and C, and 3A, 1. So there are usually 2 deep hierarchy. So for example, in the case of bank, first of all, you have to distinguish between bank the word and bank the verb. Right? To bank on something is a verb in English, and its meaning is somewhat related to the meaning of the noun bank, because it's probably derived from to trust it as much as you trust the bank. But bank can also be used when you build a embankment, when you build a fort, or you build like a trench or something like that. And then, one of the most famous examples of word sense disambiguation is the word interest. Think of how many word senses there are to interest. There is you showing interest in a topic, like you're really interested in it. There is somebody who has an interest in a case because they stand to win or lose from the case. There's, of course, the mathematical interest that you get if you deposit in your bank, your money in the bank. And if you look at the dictionary, you will find, I'm guessing, at least 10 different subshades of meaning of the word interest. One of the most helpful resources for language technology that was developed in the last 20 years is called WordNet. It sounds futuristic like Skynet. It is WordNet, started by a linguist called George, why am I blanking out on his last name? What's his last name? I'm sorry? Miller, thank you. George Miller passed away a few years ago. He won the Presidential Medal of Science, really a very distinguished professor at Princeton. And one of his life's works was creating this WordNet in English, which started as just a graph of every node is a word in English. In fact, it's not a word, it's a word sense in English. So interest might appear 10 times. One is the bank, getting interest on your money, and the other one is having an interest in something. And then, so he introduced the notion that the fundamentals of the language are not words, but word senses, fully disambiguated words. And then he created links between them if they are opposites of one another, if they are synonyms within one another, if one is an example of another, so all sorts of relationships. And then you can do and he originally populated this with hard manual work. So he and his students sat for years and coded in words, first from a dictionary, then from works, different technical works and works of fiction and so forth. And then, he had a separate WordNet for noun and one for verbs, one for adjectives, one for adverbs. And this has grown and grown, and there are now whole conferences devoted to WordNet and its uses. It exists in other languages as well. Anyway, I digress. So we have word senses, we have part of the speech tags, we have preposition, phrase, attachment. What else?
Complement by the bank.
Complement by the bank.
By the bank belongs to the school or standing.
Right, so by the bank is a prepositional phrase too. So the question is, where does it attach? Where did you subconsciously attach it? Who attached it to standing? Who attached it to saw? Now, when it's attached to saw, it's not even clear. Even there are 2 meanings. If you saw by the bank, does that mean you stood by the bank and saw? Or if you saw something by the bank? All right, so we don't need to resolve it. I just want to point out the richness of the ambiguity. What about this?
I don't know if it's Mary or Jane.
Right. How many of you thought it was Mary? How many of you thought it was Jane? Okay. So interestingly, it's a delicate question because you see something. If Mary saw her with the telescope, through a telescope, that means that she was probably far enough away that Jane couldn't see Mary. And that brings into question, why in the world would anybody wave to anybody? Like if Mary waved because she knew Jane was there, but Jane couldn't see her, or if Jane was there, she didn't see her, why would she wave to her? So there's a problem there. But this is a good example of how common sense and world knowledge and logic all play a role sometimes in disambiguation. And these are the things that are hardest for language technology to capture. We can capture things that occur often, we can capture correlations and general rules, but when you have to take into account common sense that she wouldn't see her at this distance, if she could see her, why would she need a telescope, all that kind of stuff, then that's very, very hard for us to do right now. You can also go backwards and say, because it doesn't make sense either way, it makes it more likely that the person with the telescope was Jane, not Mary. And that she was just standing with a box with a telescope in it. She just bought it in the store. Mary saw her from pretty close by and waved to her. So this is called a pronoun. Pronoun. She, he, it, they, and so forth. And a pronoun, and what we do with pronouns is pronoun resolution. So we need to understand that this refers to a female, most likely human, but not necessarily, and find possibilities here. It could be Mary or Jane, and then the same thing here. And then we have this highly contextualized problem that we have to resolve it so that one of them points to one and one points to the other. So you cannot say that this has to be Mary and independently says that this has to be Mary. The solutions are either this is Mary and this is Jane, or this is Jane and this is Mary, right? So they're dependent on one another. They're very context sensitive. Okay, and then the deeper thing we can do with this is build a whole tree, which some of you might have done in grammar school or in middle school with like a tree that includes subject and object and verb and all of that. So let's do it here because that's a large part of language. I don't remember what you call these trees. Parse trees, maybe? So you can parse the entire thing, and you have a sentence, and it goes into a subject, noun phrase, and a verb phrase. Doesn't have to, of course, but this is a very common way that sentences break, noun phrase and verb phrase. So the noun phrase here would simply be Mary. And then the verb phrase would be a verb and a noun phrase again. So the verb would be saw. And the verb phrase would be everything else up to the word by the bank. And what did she see? She saw noun, which is Jane, and maybe a prepositional phrase. So this is Jane. And the prepositional phrase was standing with the telescope. So I don't want to commit to it because I don't know enough grammar to know what are reasonable, but a few comments about that. One, this is a fairly difficult job to do. We teach it to middle school kids, but we teach it with simple examples. The more important thing is that reasonable people and even intelligent, educated, expert people may disagree. There are different ways for some sentences to say, oh, I think it's better listing it that way or listing it that way, above and beyond the disambiguation of the meaning. Even if you have a meaning, there is no one ground truth of what the correct parse tree is for that meaning. Some of it is a matter of convention. So now back to our notion of a surface form. The surface form is just sequential list of words. Each word can be represented by an index into a vocabulary, or alternatively, it's just a sequence of letters. So there's nothing exciting there. But hiding behind it, we imagine, is this hidden form that includes all the fully annotated richness of the meaning, and maybe even of multiple possible meanings. Let's say just one meaning. So it might include the parse tree. It might include the part of speech of each word, or the correct part of speech for each word, the attachments, which phrases attach where, the pronomial resolution. She means Mary, her means Jane. It will include, of course, the word sense disambiguation. In this bank, we mean the financial institution, and so forth. So now let's go back to statistics. Let's imagine that there is a distribution in the world out there that is a joint distribution over both the surface and the hidden part. And for short, I will call it P of S and H. So if we talk about sentences, imagine you push a button and out comes a pair, surface and hidden. Let's say you can see the hidden now. You're sitting from above and you see that. And of course, they're not independent of each other. For any given surface form, there may be multiple possible hidden forms depending on the interpretation or the disambiguation. And for every, opposite is also true, for every fully annotated meaning, you might possibly be able to express it in a different set of words. For example, some of the prepositional phrases can come in different orders. Right? Sometimes adjectives can come in different orders. Interestingly, some languages allow you to use adjectives in any order you want. Some languages impose constraints of which adjectives come first. But generally speaking, there is freedom. If you're given the desired meaning and the fully disambiguated message, there are multiple surface forms that can express it. Okay? So there is a relationship between the two, but it's not a one-to-one relationship. Now imagine that we hold in our hand this magic tool that gives us the probability of every particular pair. This tool can now be used to do a lot of things. It will take all computational linguists out of a job and pretty much all language technologists out of a job, because it solves both problems. And I will define for you what computational linguistics and what language technologies problems are. So I'll start with computational linguists. Computational linguists are usually, some of the tasks they deal with is the tasks that we described here: word sense disambiguation, preposition phrase attachment, parsing. All of these things, solving these problems, are known as computational linguistics problems. So you can think of computational linguistics as, also goes by the name compling, as taking a surface form and mapping it into a hidden form. How am I going to map a surface form into a hidden form if I have this magic tool here? Here's how I'm going to do it. I'm going to say that the correct hidden form is the one that maximizes over all possible hidden forms the conditional probability of the hidden form given the sentence, given the surface form. Because this kind of a problem means you're given S, you need to derive H. So one reasonable way to proceed is to say, condition on knowing S, which H is most likely. I know S, I saw it in writing, there's no question about it. In a world where I saw S, which H is most likely? It doesn't mean you'll always be right, but it's a reasonable heuristic to give the one that's most likely. I still didn't give you this, but I guess you know that you can easily write it as P of H and S over P of S. And P of S can be written as sum of P of H and S over H. So this is called marginalization. You take a joint distribution, you sum over one of the variables, and you get the marginal of the other. And this is simply the definition of conditional distribution. So we're getting a little practice in conditional distributions, joints, marginals. So my claim is that if you have only this, only the joint, from it you can derive a marginal and a conditional. And if you have a conditional, you can provide a reasonable answer to this question. Now I presented H as if it's a one thing, it's a complete annotation of everything. But computational linguists usually don't try to solve everything, they try to solve one problem at a time. So you can also think of H as only providing, let's say, the word sense ambiguation for one particular word. But the same framework applies. H will consist of all the possible senses of the word interest, and S will consist of a complete sentence or even a whole paragraph or document that has the word interest in it. And P of H given S means, given that particular surface form, everything you know about it, what is the probability of every one of the possible senses of the word interest? And H star will be which word sense has the highest probability. Question?
We're given S. Isn't P of S going to be constant or the marginalization of that? So wouldn't we only need to look at the numerator of that second equation, like the joint distribution here?
Absolutely.
Because we keep the mass.
Absolutely. So yeah, we will discuss it in more detail later, but yeah, absolutely. So notice that we're maximizing over H here, and P of S does not change as you change H. So whichever H maximizes this also maximizes this. This is a constant with regard to maximization. We'll talk about it again and again later. So, but the point is, if you have the joint, you can derive everything from it. In principle, remember that these spaces are huge, so computationally it may not be possible, but conceptually. All right, so this is what computational linguists do. Now there's another breed of researchers called natural language modelers, or language modelers. And their interests are a little different. Language modeling has to do with simply estimating the probability of surface phenomena. Just S. So how do you do it, and what is it good for? How do you do it? It's much simpler than that. It's simply, if you have the joint, you just marginalize it over H. Right? So from the joint we can satisfy both the computational linguists and the language modelers. A more interesting question is, why would you need it? I mean, if we live in a world where the S part, the surface part, is known and incontroversial, why would we need to know the probability of what we saw? And the answer is coming up. I'll give you examples of when we use it. But we will do a lot of work on estimating just this. And again, when I say this, in principle, this S could be any surface unit of language. But sometimes it could be just variations of it. Like, just like here we said that H could be just the word sense of a particular word in a sentence. The same thing could be here. You can think about it as the probability of some word occurring in a sentence, or of some word occurring more than twice in the paragraph, or any kind of phenomena that the answer to which is clear from the surface. We might be interested in that too.
Do you need a hidden variable in the case of language modeling? Is it something which is required?
It's a good question. It's required in order to do better, so it's useful. But no, you don't. I mean, you can say everything is equally likely and go home. Right? In that sense, you don't need it. But to do a good job, yes, I think you do.
But aren't surface forms just enough? Like, even when you take conditional probabilities of sequences of words in a given sentence in terms of language modeling, you're not investigating anything hidden, say, part of speech tags. But that's still language modeling.
Standard n-gram, I'm not doing anything latent or hidden. But arguably, you could do better if you use latent variables. Just to give you quick examples, if you have a latent variable which is the topic, it can influence the n-gram as it goes along. Okay, so let's now look at specific examples of where language models are used, and in general, how language technologies benefit from this kind of framework. So my first example is from speech recognition. So example 1, speech recognition. In speech recognition, the input is some acoustic signal which I'll call A for acoustics. There's a lot of work that goes into signal processing, how to represent it, but that's all going to be just an abstraction for us. There's some acoustic signal. The output is some piece of language, maybe a sentence, maybe a few words, maybe a single word. A fragment of language. And specifically, it's a fragment of text, but here I'll just call it language. Of language. I'll call it L. So speech recognition can be thought of as mapping A to L. How am I going to do this mapping? Very similar to what I did there. I'm going to tell myself a story. When my microphone picks up the acoustic recording, I'm going to say to myself, this acoustic recording used to be a piece of language, used to be a piece of text. But something happened to it along the way. It got mangled and processed and got converted into an acoustic signal. So this way of thinking is called the source and channel framework. This is my channel and this is my source. In the source there was a language, a piece of language, a sentence. And this is the channel. And out comes something different, acoustics. Notice very significantly that the order here is from L to A, whereas the order of our original problem is from A to L. We reverse the order. One might say we reverse the logic. The logic here makes sense. Really, whenever you hear spoken acoustic signal, it did come from somebody wanting to express some language. So it actually makes a lot of sense to do that. There will be other situations we will do it that may not make much sense to you. But I start from speech recognition because here it's perfectly reasonable. So we say once there was a source of language, and that source produces some language, some piece of language from a distribution. Which distribution? Oh, I erased it. From the P of surface distribution, or P of L language. And that language went through a process, which is our thinking process, our grammatical structures in our brain, converted into particular words. So maybe it already came as a sequence of words, and it went through a phoneme choice and articulation, and producing it through our mouth, and out came acoustic signal. And now all we see is the acoustic signal, and we want to deduce what was L that caused it. So we see the outcome, and we want to work backwards to what the source was. And where we're going to do it, and it's going to be common to all of the methods, look like this, is we say that our choice hypothesis, I'll always mark it with a star, our best hypothesis would be the one that is most likely given the acoustics, given the evidence that we saw. So it's defined as argmax over all possible linguistic candidates of probability of the language given the acoustics. I'm going to rewrite this as argmax. Now I'm going to use Bayes' formula. Do you remember in Bayes' formula we reverse things? So it's going to be argmax of P of L times P of A given L over P of A. When we did Bayes' formula, we had two very different things. We had parameters and data, and therefore the probability of the parameters was called the prior, the probability of parameters conditioned on the data was called the posterior, the probability of the data conditioned on the parameters was called the likelihood. Remember, they all have names. Here it's a little bit more mixed because A and L are kind of the same kind of creature. But the formulas are still correct. It's a general trick for reversing dependence. I started with how L depends on A, and I ended up using something like how A depends on L. To convince yourself that these are the same thing, notice that if you move this to here, you get P of A times P of L given A, which is the chain rule. So that's the joint probability of A and L. And here you get P of L times P of A given L. Again, it's the joint probability of A and L. So it's the same trick I used before. I'm just using two different derivations of the chain rule and then moving one thing over. So the next thing I do is, the comment that I got earlier, is notice that P of A is not part of my maximization. I don't really need to calculate it. It's fixed. It doesn't change as L changes. So I can cross it out, and I'm left just with this. And now I need to plug in here reasonable numbers. So I'll start with this. This is my language model. This is what I promised you earlier when I talk about language models. Why is it useful? Here's one place where it's useful. It's useful because we're going to probe it with many, many different alternatives, and it's going to plug in here a value for them. Before I talk about how we estimate it, let's just see what roles they play. This is a prior over language. Prior over language. So this tells you, if you're considering multiple hypotheses, some of them may be more likely to have been said a priori before you heard anything. You know, some sentences are more common than other sentences, right? This part deals with the degree of match between a particular linguistic candidate and the acoustics that we saw. This is more complicated. Well, it has two different kind of creatures. One of them lives in language space. The other one lives in acoustic vector space. So not surprisingly, I would say 70 to 80% of work in speech recognition goes into estimating this. This goes by the name acoustic modeling. Now, why is it called acoustic modeling if it has both acoustics and language? It should really be called acoustic linguistic modeling, because it's modeling the acoustics conditioned on the language. But the emphasis here is on the acoustics. If you really wanted to model purely acoustic, you will be modeling P of A. And there's room for doing that too. That means some acoustic signals are more likely a priori, regardless of what is said. Some things sound more like speech than others. That's what this would do. This work starts with any particular sentence, converts it into a sequence of words. Each word is converted into a sequence of phonemes. And there could be many ways of converting into phonemes. Each phoneme is converted into a distribution over possible sequences of acoustic frames. So this is a very probabilistic kind of top-down that takes a language and takes a sentence and converts it into a distribution over acoustic signals. And that's all estimated from data in a way that we will touch on in this course. This seems a little simpler, and it's the junior member of the coalition. I would say maybe 20% of work in automatic speech recognition goes into modeling the prior over the language. This 80-20 is just a rough estimate based on maybe number of papers published or number of people working in the field. I actually, when I started working in the field, I started working on language mostly because it was such a small, isolated, not much competition. Since then, it became a lot more competition because the field grew as a whole, but it's still the minority place. And I didn't have to learn much about acoustics. I could just focus on language. So if we had the right functions here, we will be done. And in some sense, this is the best we could do. Namely, not every time we're given an acoustics, we will come up with the right language for it. So these kind of classifiers are not guaranteed to give you the right answer. But in some sense, they're the best that you can do. The errors that they will make, it's called the Bayes error, and it cannot be reduced further because there's inherent overlap or inherent ambiguity in the problem. But in reality, we don't really have those. What we have instead is estimates of these things. And their estimates are sometimes not very good. In statistical theory, we designate estimates by putting a little hat over the probability function. So if you see something like P of L, that means the true, theoretically correct probability distribution that we may never know, or that we may just assume for some exercise. If you see it with the hat, this means a particular estimate of that true distribution that is based on some finite amount of data and on some particular method of estimation. Okay? So hat means estimate, no hat means the real thing. So our problem is going to be now estimate a distribution over language, estimate a distribution, a conditional distribution over acoustics given language, and then plug them into this mechanism. There is the further practical problem that this space of all possible sentences may be very, very large. So if it is large, you have a search problem. You cannot afford to enumerate all possible sentences in the language. You may need to think intelligently about which sentences to do, in what order, and how to gradually work through them. So you can say that acoustic speech recognition consists of acoustic modeling plus language modeling plus search. These are the three components of speech recognition. And when the speech recognition makes a mistake, it could be because of a problem with the acoustic model. It could be because of a problem with the language model. This is called P hat of acoustics given language. This is P hat of language. Could be because of a problem here. Could be because of a problem with the estimate of the language model. It could be a search mistake. And it could be none of the above. It could be a Bayes error. A Bayes error is when you made a mistake, but in a sense you made the best choice you could have. You just were unlucky. So to give you a quick example of a Bayes error, if I choose a number between 1 and 10, and you have to guess if my number is greater than 7 or not, and I tell you that I choose uniformly, your best bet is to always say less than 7. Right? But every now and then you'll be wrong. It doesn't mean you made the wrong choice. You still gave the best answer, but some of the time that answer will be wrong. That's a quick example of a Bayes error. That happens too. I mean, sometimes people say something and it sounds like something else, but they really meant, now we're going into undefined. What does it mean what they said, what they meant, or what somebody heard? All right, we'll leave that. All right, questions about how the source channel paradigm applies to speech recognition?
So in this real quick, but an application like Dragon by company Nuance, at the highest level, is it most likely 3?
Absolutely. Just about any commercial system, you look under the hood, there's a language model, acoustic model, and search engine. There is one other component that I didn't go into detail, and that is pronunciation modeling, mapping a word into a sequence of phonemes. If you just take a standard dictionary and you follow what the dictionary says, you will do very poorly, because people don't speak the way the dictionary claims they speak. So first of all, the way they pronounce things, of course, varies from one region to another, but it also varies over time, and it tends to not be captured right in. So there's something called the base form pronunciation, which is the way you're supposed to pronounce something. But then there is the way we actually pronounce. We drop vowels, and we combine things, and we do all sorts of weird stuff. So that's a source of headache too. So I would say we don't know how to solve that as well. So that is not usually an explicit part of commercial recognizers, but it is definitely part of research systems. There's a lot of research on how to do that mapping well. Commercial systems usually solve it by brute force. They come up with pronunciation dictionaries, and they add alternatives to them as they can. And so yeah, I would say there's also a pronunciation modeling component. It's a smaller component. Yeah.
Like use your brain, which is doesn't follow, because use and you, and when you combine some dialects, you get use your brain.
Right. That's an example. There are many, many examples of how your pronunciations changes. And then some of it happens at the sub-phonetic level, where we're not hearing it, even if we want to hear it, but it still has an impact on the recognition. But people have studied it. People have done psychoacoustic experiments and have studied how, it's called co-articulation effects. So it turns out if you say ba or pa or ka, the vowel is different. Even though it sounds to you like I said the same vowel, from a spectrogram you will see that the vowel is different. Which consonant you use affects the acoustics of the vowel and vice versa. So there's a lot of work on psychoacoustics. Some of you may be familiar with it. Really, really fascinating. Okay, so this is called the source channel framework or the source channel paradigm. Statisticians know it as simply a Bayes classifier. All right? So source channel paradigm is the same thing. Source channel is the same thing as a Bayes classifier. And what makes it a Bayes classifier is that you can identify this with the prior, this with the likelihood, this with the posterior, and this with the evidence. All right, let's do one more example. In fact, I'd like to do several examples, but we have time for just one, of a different language technology and how you use source channel model to... By the way, we don't have class on Monday. It's Martin Luther King Day, and the university cancels classes after 12:30. And since this is afternoon class, it is canceled.
Does that include classes that start at 12:30?
I don't know. I don't know. Okay, machine translation. In machine translation, you're giving a sentence in one language, let's say English, and you're asked to come up with the equivalent sentence in another language, let's say French. I encourage you to look back and forth between the two because there's going to be complete analogy here. This is equivalent to the mapping A to L. Here we're mapping creatures from the English domain to creatures from the French domain. What we're going to do is we're going to pretend that the English sentence that is given to us and that we're asked to convert into French, when it was born, when it was very little, it used to be French. It was born as a French sentence and something horrible happened to it and got converted into English. Okay?
You thinking the other way around, perhaps?
Yes, I was. But pretend that there was an F and that it went through a channel called the F to E channel, and out comes E. Now, I promised you that the speech recognition story made sense, because really acoustics did start their life as a language. But here it's kind of crazy, but bear with me. And now we see E. We know what E is, and we have to deduce or guess, because we can't be sure, what F was, what F used to be. And how do we do that? We say that the winning French is going to be the one that maximizes, among all possible French choices, the posterior of French given what we know, which is E. E is fixed. E is fixed. There's just one E. F, we're going to try all possible Fs. And the same way, we're going to use Bayes' formula, which is over F, to invert it into P of E times P of E given F. I'm sorry, this is P of F times E given F. And this would be over P of E, but it's always going to be the case that the P of E does not participate in the maximization. It is constant with regard to f, so we can cross it out. So this is the source channel framework for machine translation, also known as the base classifier framework for machine translation. One more step we need to take. We wish we had these. We don't have them. We have estimates of them, so we have to put hats here to remind us that these are estimates based on some data in some form. Is this clear? Any problems? Any wonders? Please?
So is it better to follow some processes so there is an underlying reading space between these two languages?
That's a very good question. One way we could solve this problem is using latent variables, namely say there's a space of meanings and the meaning is the same and it gives rise to an English sentence and gives rise to a French sentence. So the way we would do that would be, we will draw a little picture. There will be a meaning, call it M, and the meaning gives rise to E and gives rise to F. And now we are given E, so we have to deduce from it what is the likely meaning, and maybe we have to entertain multiple possible meanings, and each one of them gives rise to F, and again this mapping may be one to many also. And we could write that out too. And one could argue from a linguistic point of view that that might make sense. There is certainly a branch of machine translation that does that, goes through an intermediate, what's called interlingua, a representation that is artificially created to represent meaning. And you take a source sentence, you convert it into interlingua, and then from interlingua you convert it into the target language. The main reason for doing that is pragmatic. Using the interlingua method, you can, with much less effort, translate one sentence into many languages. You just have to write one converter for every one of your n languages into the interlingua, and one generator from interlingua into every one of your languages. So if you have n languages, you have 2n different pieces of code or modeling to do. Whereas if you wanted to convert from any n language to any n language, you'd have to write n squared different converters. That's controversial. I mean, this is not a machine translation class, but let me just mention that when you translate a particular pair of languages, you don't have to deal with the complexities that these languages don't know about. And you can take advantage of similarities between these languages to not have to fully disambiguate everything into interlingua. Whereas interlingua, you need to disambiguate everything. But anyway, that's a fair thing to do. Sticking with this formulation, yes?
Well, I think the other, if you want to solve the problem, you need to estimate the probability of E given F. And where do you directly estimate the probability of F given E?
Thank you. Every year, I wait for that question. And every year, it never fails to come. Thank you. So that's a very good question. Let me explain it. I said that now I need to build an estimator for this. This is kind of my language model, or my prior over French. And I need an estimator for this. This is the equivalent of the acoustic modeling. This is the mapping from F to E. But French and English are both languages. They're both about the same thing. They have the same complexity, more or less. If I know how to build an estimator for E given F, then I can probably use the same method to bring an estimator of F given E and plug it in here. Why do I need to go through this process? It made sense in speech recognition because this is much harder to think about, how to map acoustics back to its language, than this, how to map language to acoustics, because we know that the generative process of speech is indeed going from language to acoustics. We have the mechanics of it. We understand that if there are a bunch of words to be said, somehow every word is mapped to phonemes, and the phonemes maybe influence each other, and every phoneme is mapped to a particular articulation, and this causes particular acoustic wavelengths and so forth. There's a lot of study about how this happens. These are real phenomena, and it makes sense to model something real that we kind of understand how it happens. So I can totally see why this is better to model than this. But what's the difference between this and this? Just reverse the name English and French. Kali.
The second one is also an estimate, and the first one is
This is an estimate?
yes.
But if I don't do this, I can just do an estimate here, right?
You have two sources of information instead of one, so you can send, in some sense, smooth over the mistakes that your translation model makes with the language model, whereas if you estimate it directly using only a translation model in the other direction, then you don't have any prior knowledge on what is good translation, what is sort of fluent in your language.
So let me expand on that a little, and then we'll continue. We'll come up with other explanations. What I have here is breaking down of the job into two tasks. One is the goodness of fit between any particular candidate and the original sentence. And the other one is how likely is that sentence in French in the first place. And that speaks to what you said about fluency. It could be that there are multiple ways of mapping E to F. There's F1 and F2, and they're both equally close in meaning to E. And therefore, the P of E given F might be the same for both of them. But the P of F of one of them might be better than the other because it is more fluent, it is more likely to be found in a corpus of French-speaking people, and therefore it is a priori more likely. Okay, so likelihood and fluency kind of the same thing. Now, that doesn't quite explain it, because if you estimate this, so we talked about two Fs, F1 and F2. Both of them map very well into our target E, which is fixed. F1 is fluent. F2 is awkward. In our original proposal, this will be the same, because this says given an F, whether it's fluent or awkward, how well does it match our E? And the answer is that it matches the same, because they're both equally close in meaning. But this will help differentiate between them. It'll say, okay, if the person either said F1 or F2, probably they said F1, because it's the fluent, it's the more common way of saying it. So this will work. What about estimating this directly? Well, it will also work. Because if you're estimating this mapping from E to F from a corpus, you will find that in the corpus F1 occurs much more often than F2. So the conditional distribution does capture also the relative frequency of F. But we're on to something.
Yes, PF itself is a model, and we might choose to update the PF later on. So that's why we're working with PF. We keep on updating it, and we keep on working with it in our next estimation.
Right. So it allows us to split the work and to work on different aspects of the problem sort of orthogonally or separately. We can split the team and have one team work on modeling French, just a language of French, without relationship to any other language, without worrying about just the frequency of different things in French. Specifically, the bonus we're going to get is that we can go out and seek other corpora. In fact, it's much easier to get a large monolingual corpus than to get the sort of parallel bilingual courses that are needed for estimating the conditional distributions. So one team will work on this, and it's free to go out and use a lot of other data. And another team will work on this, using only the parallel sentence-by-sentence bilingual data. So that's one argument that you can make why. But the truth is you could go directly for that. The other argument is a little more subtle. It's not a mathematical argument, it's a pragmatic argument. You think differently when you think about these. So these two groups will work on different aspects of the language. Different aspects of the language distinguish goodness here from goodness here. Here you worry more about accuracy of meaning and correctness. Here you worry about how people actually express themselves. This all is kind of a hand-wavy argument, and I need to let you go. You're going to have a homework that will ask you to come up with a source channel formulation for some language technology. When it's up, we will let you know. All right? Thank you.
Will it be on Blackboard or just
My website, which will come up in the next few days, I promise. A week after it's out.